So friends, let's learn about potential energy of a dipole in an uniform electric field. In this topic, we require uniform electric field. These parallel lines give you uniform electric fields. In this uniform electric field E, let us place a dipole. So minus Q charge here, plus Q charge here, dipole. Having dipole moment P at an angle theta 1. Let us rotate this dipole. This means that if you have this dipole, rotate this dipole through a small angle d theta. So when you rotate it, let us rotate it through a small angle. This is d theta. So this angle becomes theta 2. So in this case, what will be the potential energy stored inside the dipole? You have to find this. So first of all, you know that small work done in rotating dipole to d theta is, what is the small work done? Work is equals to torque into angle. So small work done dW is equals to torque tau into d theta. The formula is very easy to memorize. You know that work is equals to force into distance. Here in the place of force we have taken angular force, and in the place of distance we have taken angular distance. So work is equals to force into distance. In the case of angular movement, work is equals to angular force into angular distance. Angular force is said to be torque and angular distance is said to be angle. Now you know that what is torque? Torque is Pe sin theta d theta, because you know torque tau equals to Pe sin theta. We have to integrate it from theta 1 to theta 2. So you have the work W is equals to integration theta 1 to theta 2 dW. This will be the total work which we require to find. Put the value of dW from this equation, which is Pe sin theta d theta here. So you have Pe sin theta d theta integration theta 1 to theta 2. So P is constant, take it out. So P, take it out, integration theta 1 to theta 2, you have sin theta d theta. Integration of sin theta is minus cos theta. So you have minus cos theta, give a square bracket here, write theta 1, theta 2. Now change this theta with upper limit theta 2. First of all, take out this minus sign outside, so it is Pe. Now change this is cos theta 2 minus cos theta 1 lower limit. This is said to be work, and this work is stored in the form of electric potential energy U, capital U. So you have this work is stored in the form of electric potential energy U. So you can write therefore U is equals to minus P under bracket cos theta 2 minus cos theta 1. This will be the required formula here. This is the required formula. So thus you learn what will be the potential energy stored inside the dipole. Now if I said that I am starting the rotation from 90-degree angle, this is the 90-degree angle, then angle theta 1 is 90 degree, and let it is rotated up to a given angle. Let the given angle is theta. In that situation, we have slight change in the formula. This means that when theta 1 is equals to 90 degree and theta 2 equals to theta, then what happened? Then U is equals to minus P cos, here it is theta 2 is theta, minus cos, here is theta 1 is 90. You know that cos 90 is 0. you know that cos 90 is equals to 0. So you have minus p cos theta. This can be written as minus p dot t dot product, because you know that a dot b equals to ab cos theta. You know a dot b vector is equals to ab cos theta. So reverse is also true. If you have written ab cos theta, then this means that a dot b. So here it is pe cos theta, we have written p dot t. So this is the desired equation for electric potential energy. Now let us see few cases based on electric potential energy. You have case number 1. In this case, electric field and dipoles are kept parallel to each other. This means that in this situation, this is electric field E and this is dipole P. So these two are parallel to each other. So in this situation, theta equals to 0 degree. Theta is equals to 0 degree. So you have U is equals to minus PE cos 0 degree. Cos 0 is 1. You know that cos 0 degree is equals to 1. So you have this is equals to minus P, and this is the minimum value of potential energy. Minimum value of potential energy. So you can write it in UMIN minimum. So this is the minimum value of potential energy. Therefore you have UMIN minimum is equals to minus PE. Minus PE. So here we have minimum potential energy, and this is said to be stable equilibrium. So this is said to be stable equilibrium. Now you have case number 2. In case number 2, this dipole is kept anti-parallel. So theta is equals to 180 degree. Theta is equals to 180 degree because both are anti-parallel. So in this situation, you have cos 180 degree here. Cos 180 degree equals to minus 1. So you have minus 1 here. So minus and minus, this become plus P. This is said to be U max, maximum potential energy. And this is said to be unstable equilibrium. This means that when the energy is minimum, it is said to be stable equilibrium, and when the energy is maximum, it is said to be unstable equilibrium. Now let us learn the third condition. In the third condition, number 3, I am placing the dipole perpendicular to the electric field like this. So this is P. So this is equals to 90 degree perpendicular. So here you have U is equals to minus P cos 90 degree, and cos 90 is 0. So you have minus P into 0 equal to 0. Thus you have learned about electric potential energy in rotating a dipole in a uniform electric field and their cases for zero potential energy, stable condition and unstable condition. That is, when the energy is minimum, it is said to be stable equilibrium, and when the energy is maximum, it is said to be unstable equilibrium. Now let us have numerical based on this. First of all, a very simple numerical. Okay. Now the numerical is, here we have a electric field E and here we have a dipole P. So angle between these two, that is theta 1, is equal to 0 degree. Let us rotate this dipole. We have rotating this dipole. When you rotate this dipole will rotate to this direction. So this becomes the new position. So now the angle between these two become theta 2, which is equals to 180 degree, because these two are parallel. here these two are anti-parallel, and here these two are parallel. So what will be the potential energy in doing so? This means that we are placing a dipole parallel to electric field, rotating the dipole anti-parallel, then what will be the energy stored? For this you have U is equals to minus P cos theta 2 minus cos theta 1. So it is minus P, what is theta 2? Theta 2 is anti-parallel, so it is cos 180 degree. And what is theta 1? It is parallel, so it is cos 0 degree. Cos 0 is 1 and cos 180 is minus 1. So you have 1 here, you have minus 1 here, and you have minus P this side. So this is minus 1, minus 2, minus come out, and this become 2Pe. So potential energy is 2Pe. Let us have another numerical. Numerical number second. In this numerical number second, this is electric field E, okay? And here we are placing a dipole moment P. Then for producing a dipole, we require a charge. Let the charge is minus 8 nanocoulomb this side and plus 8 nanocoulomb this side. So this become an electric dipole having separation of 4 centimeter. Separation of 4 centimeter. Then you know that the torque will be in this direction because it rotates, because we put our right hand on P and move our hand towards E. So the torque will be inside the board. So this is the direction torque, and let the torque is 4√3 Newton meter. Now in this question you have to find what is the magnitude of electric field E and what is potential energy U in this question. So how we are going to solve it? First of all, we require the dipole moment P. So you know that P equals to Q into 2A. What is Q? 8 nanocoulomb. It is 8. Nano means 10 to the power minus 9. And 2A is, this is 4 centimeter. So 4 into 10 to the power minus 2 in meter. 8 into 4, 32. And 10 to the power 9 and minus 2 is minus 11. This is coulomb meter, the unit of dipole moment. Now you have the formula torque tau equals to Pe sin theta. Let the angle is also given to you. Angle is 60 degree, okay? Then since angle is 60 degree, so you have torque is equals to 4√3. Here you have P is 32. 10 to the power minus 11. E you don't know. Here you have sine 60 degree. So when you cancel this 4, you have 8 here. So you have √3 is equals to 8 into 10 to the power minus 11 into E, and sine 60 is √3 by 2. So you have √3 upon 2. So from here you cancel this root. So you cancel this 2. You have 4 here. So what will be electric field? Electric field is 1 by 4 10 to the power minus 11, which means 1 by 4 means this is 0.25 and 10 to the power plus 11, which you can write 2.5 10 to the power 10. Unit of electric field Newton per coulomb. Thus you find the value of E. E is equals to 2.5 10 to the power 10 Newton per coulomb. Now next you have to find U. Just you have learned the formula for U is equals to minus Pe cos theta. So you have minus, what is the value of P, which we have find out? P is equals to Q into 2A, and Q is 8 into 10 to the power minus 9, and 2A is 4 into 10 to the power minus 2. So this is 32 into 10 to the power minus 11 coulomb meter. So you have P equals to 32 10 to the power minus 11 coulomb meter, and electric field E is 2.5 10 to the power 10, and here cos 60 degree. So here you have minus 32 10 to the power minus 11. This 2.5 can be written as 0.25 10 to the power 11, and cos 60 is 1 by 2, that is half. So you have minus 32, this 11 and this 11 will cancel out. 0.25 means 1 by 4, it is 1 by 2 here. You cancel this by 4, so you have 8 here. You cancel this by 2, so you have 4 here. So you have minus 4 joule. So potential energy equals to minus 4. Minus sign indicates that the energy is stored. Minus sign indicates that the energy is stored inside the system. So U is energy, or you can write like this. This means that potential energy of dipole is 4 joule stored in the system. Thus, you have learned what is the expression for potential energy of a dipole in rotating in a uniform electric field, and how to solve different type of numerical based on this. Do like, share and subscribe my channel, that is Physics Gold Ravi Kumar. Thank you.